something called in 8.1 sampling distribution of X bar, which is the sample mean as we know it. And in 8.2, the same thing, sampling distribution of proportions. So today we're going to focus on 8.1, sampling distribution of X bar. So 8.1. So what is a sampling distribution? First of all, sampling. It comes from a sample. Sampling distribution is the probability distribution, is a probability distribution. And since we're talking about X bar, we are going to discuss the fact that if we collect many samples of size n from a population, why many? We want to study the population, and we cannot get to everybody. It's not a census. We don't have the resources to come to everybody's door and ask them about their height or weight or blood pressure. We cannot do that. So we will collect many samples of size n from the same population. And from the first sample, we're going to get an X bar coming from the first sample. We're going to determine the mean. From the second sample, we're going to get the second X bar, and so on and so forth. Many samples of the same size. All of them have size n. And this is a new random variable. So this new random variable, denoted by X bar, we will notice that this is also normal. Regardless, and you will see I separated from a normal population and from a non-normal population, will make no difference. So this will always be normal. So the distribution, when we look at these numbers that we determine, for each sample we determine X1 bar, X2 bar, X3 bar, all the means for each sample. This new random variable, these numbers, create a normal distribution. Well, what is the mean and what is the standard deviation, however? The mean is the mean of the population. So the population is normal with some mean, mu sub x, and some standard deviation, sigma sub x. This is the population. And you can say, but we don't have it. That's true, we don't. But if we select many samples, simple random samples, not just samples, simple random samples, very representative of the population, done correctly, selected correctly, randomly, and so on and so forth, we will notice that the sampling distribution, this new random variable that has these numbers, these are the entry, these are the data, this is the data set, will have the same mean with the population mean, but not the same standard deviation, however. The standard deviation of this new random variable will be sigma x, sigma sub x, the standard deviation of the population, but divided by the sample size with a square root on it. And I put here two notes for you. As n increases, the standard error, this is also called the standard error. So when we talk about the standard deviation, we know we talk about this. So let me write it again for you, standard deviation. But sigma sub x divided by the square root of n is also called, if you want, is the standard deviation of the mean. We can say that. But we prefer to say the standard error. Standard error of the mean. Yes, same thing with standard deviation of x bar. Same thing. We need to know the terminology in case we come across a problem that says find the standard error. And we should say, oh, what is that? Well, the standard error of the mean is this. So the higher the sample size, the smaller this number will become. And the less spread we will have. And so what? What am I accomplishing with this? I'm getting closer to the mean. I'm getting closer and closer with this to the mean of the population. Okay, so let's see how this works and what is the difference between last time. Because last time we looked at the normal distribution and we did not talk about any of this. We said there is a population that is normally distributed with mean and standard deviation. Find this, find that. Find the percentage or the probability of greater than, less than, in between. Now, all of a sudden, we are talking about another variable, which consists of repeating the experiment many times with the same sample size every time and determining this artificial number. This is not a number that I observe. This is a number that I create. Each number is the mean of the sample. So we have to be very careful when we read the question. So in example 2 that I wrote here is the IQ, which is X, of humans is approximately normally distributed with a mean. So this is our next example. Maybe the first example, I should say, in this chapter. So we are told that X, not the mean, it says X is approximately normally distributed with mean of 100 and standard deviation 15. Okay, so it means that mu sub X is 100 and sigma sub X is 15. Compute, and now we have to read very carefully, compute the probability that a simple random sample of size n equals 10 results in a sample mean greater than 110. So you erase all this. I'm going to tell you what that means. So this time we're asked not to find this, no, but to find this. Compute the probability that a simple random sample of size n equals 10 results in a sample mean greater than 110. So please change that into what I wrote here. Sorry, my apologies. I'm not sure why that happened there. Okay, I know how to do this because the distribution of X is normal. I know immediately that X bar will also be normal with the same mean, but a different standard deviation, which will be the 15 divided by the square root of 10. And I know how to compute this using the graphing calculator with normal, cumulative density function. And since it's greater than 110, infinity, the mean, which is 100, and the standard deviation, which is 15 over the square root of 10. And this is exactly how I would enter it in the graphing calculator. Where's my calculator? Here it is. So go back to second and distributions. Scroll down to number 2. The leftmost point is 100. The rightmost point is infinity. So it's second and the comma, and put 99. The mean in our case is 100. You do not have to calculate this separately, just enter it as is, no matter how it looks in your calculator, divided by the square root of 10, and just enter. And I enter again, and I get 0.4999999. So approximately 0.49999. Oops. Did I enter 110? I entered 100. Very nice. Sorry. 110. I entered the 100 by mistake instead of 110. It's 110. I wrote 110 here, but I entered 100. Don't ask me why. And the answer is not on this, it's here. Okay, so I'm checking now. 110. Where are you, Sean? 110 to infinity. Now I have to check everything. 100, yes. The square root of 15 over the square root of 10, yes. So I pressed enter and I got 0.0175. Any questions? It turns out that even if the distribution is not, the x bar is not normal, if x is not normal, it turns out that x bar will still be normal. The distribution of x bar, or called the sampling distribution of x bar, will still be normal with the same mean and the standard deviation over the square root of n. So this is so-called the central limit theorem. As n increases, the sampling distribution of the sample mean is still normal, regardless of the shape of the population, regardless whether the population is normal or not. Any questions before we look at example 3? Okay, example 3. The mean weight gain during pregnancy is 30 pounds, they say, with a standard deviation. So the mean. So this is a population with a mean of 30 and a standard deviation of 12.9. I should not write normal because I don't know, it doesn't say. So I'm going to erase the normal. So the problem says it's a distribution with a mean of 30 and a standard deviation of 12.9. Okay, we don't have any more information about it. It says even, furthermore, it says weight gain during pregnancy is skewed to the right. So we cannot even say that's normal. An obstetrician obtains a random sample of 35. Okay, n equals 35. Fine. Low-income patients and determines that their mean weight gain during pregnancy. So from here, x bar is 36.2 pounds. Find the probability that the random sample of 35, a low-income patient has a mean weight gain of at least 36.2. Okay. Identical with what we covered, what we did on the previous example. So it's that x bar is greater than 36.2. Even if I write greater than or equal to, it will make no difference because this is a continuous random variable. So one or the other will be the same. So again, I'm using the Normalcdf in the graphing calculator. I start with 36.2. I go to infinity. I put the mean. So remember now x bar, I have to write it just to make sure it's clear. This is guaranteed to be normal. That one not. So with the same mean, but the standard deviation or standard error of the mean is 12.9 divided by the square root of 35. So here I have 12.9 and comma, sorry, 30, I didn't write 30, comma, 12.9 over the square root of 35. So let's enter it carefully. I'm not talking to you, I'm talking to myself. So normal CDF, leftmost point, 36.2. I still have the infinity in there in this calculator. The mean is, one more time, 30. But the standard deviation, because we're talking about a sample, the standard deviation is or the standard error of the mean is the standard deviation of x divided by the square root of n. So 12.9 divided by the square root of 35. And now press enter. I'm checking again. Yes. 0.0022. 0.0022. So when we look at the distribution of x bar, this is what we see. So this is x bar. The mean is 30. And so this is the mean. And the standard deviation is, I didn't calculate it, I didn't need it to, but now I'm going to calculate 12.9 divided by the square root of 35, just to see what it is. 2.18. So this is a normal curve. It's a normally distributed random variable with a mean of 30 and standard deviation of 2. Both of them are in pounds, of course. And the probability that, let's say this is 36, the probability that a sample, not one person, that the sample is greater, mean weight is greater than 36.2 is 0.0022 or 0.2%. And my question now is, do you think that this is unusual? Well, the pediatrician should look at their diet, etc., etc., etc. But for such a percent, do you think it appears to be unusual?
Yes.
Yes, I agree. I would consider that it's unusual. Very good.